gets into it. So that it should be digestible by all the young students also. I will be fine if you interrupt me for the questions at any time. Or if you want to ask all the questions in the end, that is also fine. The only thing I would request you to make this session interactive. On a few occasions, I may stop and talk to you, and I will expect that you will respond to that, whatever question or query I have from you. So, and another good thing is that this talk is not going to be very lengthy. If you start feeling bored, you can let me know and then we can stop it. Total number of slides are anyway 26. That itself should not take lots of time. So now I will be going into the present mode, slideshow mode. I will request somebody that if there are any questions in the chat box or there are any hand raised, then you would please let me know. Because I will not be able to look into the chat box with the slides on. Alright. So this talk we are going to have is about the discovery of gravitational waves. We have been hearing this in the news, the research news also, and in other places for past around 5 years now. So we know that we have discovered the gravitational waves. But the question is, yes, all right, we have discovered the gravitational waves, but what they are and what we do with them. So these are the two main questions we will be trying to address in this talk. What gravitational waves are, where do they come from, and how are they important, especially as far as the astronomy is important. So we will start with a very simple introductory fact that whatever we see around us is basically consequence of 4 fundamental forces. In other words, you can say that whatever interactions are happening, mainly among the particles, are basically happening because of this. So whatever phenomena we see around us are also because of these fundamental forces. The first one, we come across in our everyday life also, electromagnetic force. For example, this tube light is basically coming because of electromagnetic interactions. The fan also rotates because of electromagnetic interaction. Our mobile phone, our TV, all they use electromagnetic signals. So this is a force that acts between the electric charges. So the entities should be charged. And we know there are 2 kinds of charges possible. One is positive charge, one is negative charge. If the particles are neutral, then there will be no electromagnetic force between them. And when the charges are static, we feel the electrostatic forces. When they start moving, they start producing currents, and then current themselves could be a function of time, function of space, which give rise to the magnetic field and so on. So first fundamental force is the electromagnetic force, which is supposed to be a very strong force. And this is also known as the long-range force. The electric field decays as 1 by r square, the potential decays by 1 by r, which means that it can be felt up to the large distances. If I have a charge here and I have another charge far away from this charge, then they can still interact. Second force is a strong force. Do not worry about the nomenclature there. You will learn them when you go to your higher courses. For example, you have a course on electricity and magnetism. The strong and weak forces you will learn when you learn the courses like nuclear physics and high energy physics or particle physics. So we know inside the nucleus is made up of, nucleus is a central part of the atom, which has a neutron and proton inside it. All the electrons are orbiting around the nucleus. There are no electrons inside the nucleus, only protons and neutrons are. And we know that protons are basically positively charged. So when you try to pack more and more protons inside the nucleus, then they will try to repel each other. Right? So the strong forces which holds the nucleus together due to this strong interaction, and the weak forces become active when as I told that when number of protons will increase, then they will start repelling each other, and then they will try to move away from the nucleus, or basically lose the energy sometimes in the form of alpha, beta, and gamma rays, and we call them as radioactive decays, and the phenomena is radioactivity. The another one, which is a universal one, is the gravitational force, and which we already have come across in our school's curriculum. And for this, any two mass objects, they will experience a force, and that force will be an attractive force. This force is basically responsible for the gravity. Gravity means the pull which we are experiencing from the Earth. So in this talk, we are going to focus on this last fundamental force, which is gravitation. So this we know, the picture on the left hand side. It should be on my left hand side, I don't know. It should be on your right hand side, probably. So there are two masses, M1 and M2, and they are separated by a distance d. And Newton gave this formula, empirical formula, that they will experience a force, which we represent as Fg, is equal to G M1 M2 upon R, G M1 M2 upon d square. The G being the constant, universal constant of gravitation, and this force will be acting along the line joining the 2 points, and this will be an attractive force. So this picture we have. So Einstein described gravity as a force. That this is a force by which the two mass bodies, they pull each other. And then he extended this law to explain the formation of our own solar system, and the same law applies to the formation of, I'll say, galaxies, stars, and other things. So basically this law, this gravity, is not present only on the Earth. So this was a kind of unification of the laws which govern the phenomena happening on the Earth and phenomena happening outside the Earth. So this is a picture of the solar system. Sun is supposed to be center of our solar system, and then there are 8 planets. Pluto right now is not a planet, but this has a fortune of coming in and going out from the class of the planets. Earth is also there, so Earth is, we know that it is orbiting around the Sun. So this was very nice theory, which explains so many phenomena, very, very successful theory for many, many years. But then people, especially Einstein, he started realizing the problems with the gravity. Gravity picture, the picture of gravity given by the Newton. The first observation was that the forces between two bodies is this, Gm1 M2 upon d square, and this force is instantaneous. What do I mean by instantaneous? That if I remove this body, M2, then M1, for example, let's say that this is M2 is our Sun and M1 is our Earth. Earth is rotating around the Sun. The moment I take out the Sun, the Earth should instantaneously know that there is no Sun, and it should not be experiencing any force at that very instant, the moment I remove the Sun. And then it should start taking another path. It will not now go around the orbit. But that does not happen, because Einstein said that the information that the Sun has been removed will travel to the Sun in a finite time. And that time will be the distance between Sun and Earth divided by the speed of light. So the speed of light is the ultimate speed. Nothing can travel faster than this. No information can travel faster than this. So this will take a finite time. While for instantaneous travel of the information, you will need the speed to become infinite, which is not possible. So that's one major drawback, one major observation, theoretical observation drawback in this Newtonian gravity. On the right hand side, you see another thing which again Newtonian gravity was not able to explain. This is very exaggerated picture. So what they are showing that Earth is not following the same orbit around the Sun. It is constantly drifting its orbit to some other orbit, even over a one cycle. So some of these things were also not explained. This phenomena was basically observed for Mercury, which is a faraway object.
So, excuse me.
Yes.
Sir, we cannot hear you properly because of echo.
I see. Okay. Let me try to change my mic then.
Yeah,
Give me
please.
a minute. Yeah.